it's important to recognize that the Rankine cycle, or in other words, the steam power plant cycle, is going to have some thermal efficiency that you're going to get good at calculating. You're going to be able to compute what is that thermal efficiency. It's going to be important for you to remember that that's not the maximum possible thermal efficiency that can be achieved in theory. On this video, what I want to do is refresh your memory again about the Carnot cycle. So I'd like to do a little talk about Rankine versus Carnot to demonstrate to you that the Carnot cycle, it puts an upper limit on the maximum possible thermal efficiency. And then be aware that the Rankine cycle, I'm going to demonstrate to you, the Rankine cycle cannot possibly approach that level of Carnot efficiency for a number of reasons. As in terms of the recap, let's see here. Here is your tried and true schematic of a system operating in a cycle. It doesn't say if it's Carnot or Rankine or what. It just says we're taking heat in at a steady rate from TH. We're producing W dot net, and by the second law, we've got to reject some amount of heat to a low temperature heat reservoir, TL. And so the thermal efficiency is the energy sought over the energy that costs. And let's see, that's going to be W dot net sought divided by what costs you to run the plant, Q dot H. Okay, and then by the first law, the numerator becomes Q dot H minus Q dot L equals W dot net. That's the first law divided by Q dot H. And that is the way to describe thermal efficiency for the Rankine cycle. Now, what about the Carnot cycle? That is certainly true for the Carnot cycle as well. But you remember that the Carnot cycle was made up of 4 special processes in which it's the best possible that you can do, the best possible thermal efficiency you can achieve when operating between TH and TL. And that's given by, you can derive that the maximum possible thermal efficiency is the Carnot thermal efficiency, which is TH minus TL divided by TH. That's the maximum possible thermal efficiency. And so this gives you a way as an engineer to compare, well, here's what I got for the Rankine cycle, and here's how it compares to the best possible efficiency. Further, when you're talking to other people that maybe don't have a lot of this engineering background, who may think, well, the maximum possible efficiency of your plant is 100%. That needs to be your benchmark is 100%. And you can say, look, that's not the case. The Carnot cycle is the best, represents the best possible achievable thermal efficiency for a system operating in a cycle steadily. So let's see, let's remember our basic Rankine cycle components: the boiler receiving heat from TH, the turbine making power adiabatically, condensing process, rejecting heat to TL, and then finally, to complete the cycle, we need a pump to get back up to the high pressure level in the steam generator. Condenser, very low pressure level. And what did that look like? What does the ideal Rankine cycle look like on the TS diagram? Let's see, turbine, reversible adiabatic, constant pressure condensation process from some high quality X down to saturated liquid, pumping process, reversible and adiabatic, okay? And then finally, the steam generation process 4-to-1 occurs at constant pressure. Okay, so there is our Rankine cycle. There's my clockwise arrow showing that we're definitely getting some net work out. Let's visualize in the real world the required TH and TL to operate a Rankine cycle. Do you see that TH has got to be at least T1? And in many cases, it's got to be greater than T1. But at least we can write down that TH is greater than or equal to T1. right? It's the only way you can get your superheated vapor up to T1. Is your heat source has got to be at least T1. Okay, how about the condensation process? Do you see that this condensation process 2 to 3 has got to reject heat to a lower temperature heat reservoir? So TL has got to be less than or equal to T2. T2 equals T3. TL's got to be less than or equal to it. And so I've shown graphically it's right at equal to. Okay. Now let's remember about the Carnot cycle. Remember the Carnot cycle. This is basically a screenshot from a previous video where I've drawn the Carnot cycle. That was that rectangle on the TS diagram, And let's see, let's draw in TH and TL. Let's see, reversible isothermal heat addition. So here's TH sitting up right here on top of the rectangle, and TL, let's see, reversible isothermal heat rejection. So here's TL sitting right underneath the rectangle. And let's see, remember one thing about the Carnot cycle thermal efficiency, we could visualize it on the TS diagram as the area within the rectangle divided by the big area from TH part of the rectangle all the way down to absolute zero. So we've got a vision of what the thermal efficiency for the Carnot, the maximum possible thermal efficiency, is, with vision of that. And it's going to be TH minus TL divided by TH. So there's your formula, but there's your visibility of what that formula or fundamental looks like for the Carnot cycle. Remember, no irreversibilities in the Carnot cycle, no irreversibilities to be found. Let's look at some built-in irreversibilities for the ideal Rankine cycle. So even though we've got a reversible adiabatic turbine and a reversible adiabatic pump, do you see that if TH is the slightest bit bigger than T1, okay, or even down to T1, you see you've got built-in irreversibility here, even if TH equals T1, because I've drawn these red arrows to depict heat transfer across a finite temperature difference. So you're visualizing the irreversibility on this high temperature heat addition. Similarly, when TL is below T2, in other words, the river water is even slightly below the condensing steam temperature, which it will be, you've got some heat transfer across a finite temperature difference on this side as well. So visually, here's two very clear sources of irreversibility of the Rankine cycle that immediately tells you my Rankine cycle, no matter how hard I try, I'm not going to be able to get the Rankine cycle efficiency up to Carnot efficiency. Oh, and so here's a neat, I believe this is kind of a neat little view here, is you see I've drawn in my ideal Rankine cycle, 1, 2, 3, 4, and I've shaded in my net work there. And then in a pretty big green line, I've drawn in the Carnot cycle rectangle. Do you see visually? Let's see, how would the net work compare for both? Visually, the Rankine cycle net work is less than the Carnot cycle net work. So there's an explanation for lower thermal efficiency right there. And then, plus then the visualization of the Carnot thermal efficiency of this big green rectangle extended all the way down to absolute zero. That gives you an idea of further why the Carnot cycle is always going to be more efficient than the Rankine cycle. Further reductions when you have an adiabatic but irreversible turbine. So recognize here my dash line. You see that all of a sudden now I can't visualize net work because I've got a dash line, an irreversible line. I can't integrate underneath that. Okay. Similarly on the pump, this is going to be a pump that's got some type of irreversibility built into it. So there's yet a further reduction in thermal efficiency of the Rankine cycle in comparison to the Carnot cycle. And so that's my little comparison that I wanted to share with you. The Rankine cycle will always exhibit a lower thermal efficiency than the Carnot cycle. And of course, both of them are, by the second law, have got to be less than 100%. Sources of Rankine cycle irreversibilities are the heat transfer across a finite delta T from TH into the steam generator, and heat transfer across a finite delta T in the condenser as well. And then finally, turbine and pump inefficiencies contribute to further reducing the thermal efficiency of the Rankine cycle steam power plant. I hope that helps. You notice we didn't crunch any numbers in this video, but I hope it gives you a vision of thermal efficiency limitations of the Carnot cycle and then subsequently the Rankine cycle. So just good examples of the power of the second law, the limitations of the second law. And I hope that helps enhance your getting a little more comfortable with how all of this material sort of fits together.